Hey guys, we're going to talk some more about probability. Woohoo! This first part is just going to be a review from what you were doing on your last assignment, but we're going to have larger tables and more complicated problems, is really all it is. So we're going to continue with our conditional probability. So for this first example I've shown you, we have cars parked in a garage. We have three different kinds of cars. We have cars, vans, and pickup trucks. And they come in three different colors, red, white, and black, as our table shows. We're going to use that table to look at these problems. So the first thing says, if a vehicle that is red is chosen at random, what's the probability it's a pickup? So the given condition is that it's red in this case. So all we do here, and I can write it using our notation we've practiced, we have the probability of it being a pickup given that it's red. So on the top, we put our red pickups. There were 4 of those in our table. On the bottom, we add all the different red vehicles. So there's 5 cars, 2 vans, 4 pickups, and that ends up giving us 11 total vehicles that are red, and 4 of those are pickups, so our probability would be 4 out of 11. Okay. Our next example says, if a vehicle that's not a van is randomly chosen, what's the probability that it's white? So now I can write this in our notation. I can say, okay, what's the probability it's white given that it's not a van? So of all of the ones that are not a van, how many are white? And so I look at this and I add all of the ones, we can stop. We're going to do white non-vans on top, okay, because it's white non-vans. So I say 6 plus 14 on top. Then on the bottom, our condition is that it's not a van. So we're going to add all of our things that are vehicles that are not vans. So I have my 5 plus 6 plus 11, my 4 plus 14 plus 13, and then I just simplify. So I get 20. In the denominator, I get 53. And if I actually do that division, I get 0.38. A lot of times we leave probability as a fraction between, or not really a fraction, as a decimal between 0 and 1. 1 being it happens 100% of the time, 0 being it never happens. This 0.38 is the same as saying 38% of the time. Okay, so now we're going to focus some more on probability notation. I'm attaching a sheet that you definitely want to look at and use as much as possible because it kind of gives you the formulas that have to do with probability notation. Okay, so sometimes we're given probabilities instead of raw data. In all of the examples we've done so far, we've had data tables. Now we're going to just switch to we're given probabilities. In this case, we're going to use formulas to find or solve for probabilities. The reference sheet for those formulas is attached to the Google Classroom, so you want to make sure you get that. Okay, so my first example says the probability of event A is 3/4, the probability of event B is 2/3, and then the probability of event A and B is equal to 1/2. And so we want to know what is the conditional probability of B given A. Okay, so if I go and I look at my chart, it gives us a formula for that. Okay, it says, let me flip over to this formula. I'm going to kind of move the camera. It says that for any 2 events, okay, that is occurring, the probability of B given A is the probability of A and B over the probability of A. That's exactly what we're using. So I say, okay, the probability of A and B, 1/2, over the probability of A, 3/4. When I do that division, I can type it in a calculator if I want, or I can do it by hand. Remember, when you do it by hand, you flip the denominator and multiply. We get 2/3, okay? Now, in opposite order, if we have the probability of A given B, now we still have the probability of A and B on top, but now it's over the probability of B. Again, you can either use a calculator or you can flip and do it by hand. You get 3/4. Okay, the next question we're going to start talking about is, are these events independent? Independent means that they have nothing to do with each other, really. In this case, the answer is yes. If you look at your definitions that I included, it says for events to be independent, the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B, which is exactly what we found. When I look at this, I say, okay, the probability of A given B, 3/4 is equal to 3/4. 2/3 is equal to 2/3, so we're good. Another way you can check this fact is the probability of A and B is going to be equal to the probability of A times B for all independent events. So since probability of A is 3/4, probability of B is 2/3, I multiply straight across. I get 6 over 12. That's 1/2. And that fulfills that because this is 1/2. So I also know it's independent that way. Okay? Okay, now we're going to focus on using the notation and formulas. I have a lot of examples on this, kind of because I think it's a little bit confusing. Okay? So for this next example, we're given these probabilities. Now, this notation right here is new. I put it on that like formula cheat sheet I gave you. When it's written like this means the probability of A or B. When it's written like this, it means the probability of A and B. Okay, so this one's or, this one's and. Okay, and you're going to see that a lot. Okay, so we're going to use the formula. It's also on your cheat sheet. It says probability of A or B is equal to probability of A plus probability of B minus A or B. So I'm just replacing that formula with the numbers I was given in the problem. So A or B was given to us as 0.81. A is 0.67 given to us. B was given to us as 0.43. And this is my unknown that I'm solving for. So then it's just solving an equation. I added these two. I got 1.1. I said, oh, I want this to be positive, so I'm going to move this over here. And then I subtract this, and I get the probability of A and B is 0.3. Done. Okay. The next example says, given events A and B are independent with probability of A is 0.42 and probability of A, remember that's and B, is 0.35, determine the value of probability of B. Okay, so I have A and B because it's independent. Okay, so if I look at my sheet under independent, it tells me that when it's independent, we can use this fact that probability of A and B is equal to the probability of A times the probability of B. Once again, once I have my formula picked out that I'm going to use, I'm just plugging in the values they gave me. So they gave me 0.35 here, they gave me 0.42 here, and this is what I'm solving for. Opposite of multiplication, division, so I divide both sides by the 0.42 to isolate this variable, and I get that the probability of B is 0.833. Okay, last example on this stuff. It says, given the probability of A is 0.38 and the probability of B is 0.21, and remember, this means probability of A given B is 0.67, find the value of the probability of A and B. So now I go back to my probability of conditional things. I look at the formula chart, and I just copied the formula. It says A given B is equal to A and B over probability of B. Then I go and I plug in my numbers. So 0.67 is equal to the A and B that I'm trying to find over 0.21. Opposite of division is multiplication. So I take 0.67 times that 0.21 to get this answer. Type it in. Beautiful. Okay. All right, the last thing we're going to talk about today, and I think this is actually easier than the notation, is the finding the probability of independent events. So remember, independent events means the probability of one event does not affect the probability of the second event. Also remember, if you look at your formula chart, for independent events, we have the probability of A and B is equal to the probability of A times the probability of B. Okay, we're going to do a few examples and call it good. Alex has 9 t-shirts. 3 are blue, 1 is pink, 2 are white, 1 is gray, and 2 are green. Probability of rain today is 35%. These are independent events because what Alex wears will not impact if it rains, okay? So what's the probability that Alex wears gray and it does not rain today? So the first event is that he wears gray. That's probability of G. 1 of his shirts out of 9 is gray, so that's a 1 out of 9 probability. The next event it talks about is that there's no rain. Now, we were given the probability of rain is 35%. So we say, okay, we do 1 minus, move that decimal twice, 0.35, because if this is how likely it is to rain, this is how likely it's not to rain, okay? And now we say, okay, according to our formula, we take the multiply the likelihood of each event to get the likelihood of both happening. So likelihood of gray shirts and no rain, I take the 1/9 I found times the 0.65 I found to find out there's a 0.072% chance that he'll wear gray and it will not rain, which is the same as saying 7.2% chance. Okay, last example. It says, what's the probability that Alex wears blue and it rains today, or that he wears white and it does not rain today? Okay, so I'm going to start with the first situation, the probability that he wears blue and it rains. So there were 3 shirts out of 9 that were blue, and we said there was a 35% probability it rained. We multiply those, that's what our formula shows us, and I get a 0.117% chance. Second situation was he wore white and there was no rain. We already found that no rain is 65% if this is 35%. There were 2 shirts that were white out of 9. times the 65% chance of no rain. Remember though, we always leave that as a decimal, and I get 0.144. Now, remember when we do or, this is from the earlier, we just add. So we say, okay, the probability it is blue shirt and rain, or the probability white shirt and no rain. And I took those two individual numbers, I added them, and that gives me a 0.261% chance overall that either of those will happen. Okay, beautiful job. Way to go.